Now moving on to the second type of melting. We've talked about decompression melting. Now we're going to talk about flux melting. Flux melting occurs when volatiles like water, H2O, help break chemical bonds within minerals, and this lowers their melting temperature, right? So volatiles, remember, those are the substances that easily evaporate, they easily turn to gas, they easily volatilize at relatively low temperatures. So if you add a volatile, such as H2O, you can cause those chemical bonds to break a little easier, and rocks can melt at a lower temperature. And this is due to flux melting. Okay. Now, obviously, this is going to be really common anywhere you have a lot of water in rocks, and you can get a lot of water in rocks in oceans, right? Enormous volumes of ocean water is circulated through the crustal rocks in the ocean. And this water isn't just, just like hanging out in cracks, right? It's not that the water is separate from the rocks. Instead, over time, the water is actually incorporated into the minerals within the rocks. So the minerals become hydrous. That H2O is incorporated into their chemical structure. So these hydrous minerals that are formed on the ocean floor will be subducted deeper and deeper and deeper down into Earth at subduction zones. And when this happens, the water that's in those minerals will undergo metamorphic reactions. That water will be released. That water that was once in the oceanic crust will now be released into the mantle below the continent, causing the mantle below the continent to start melting. So this is actually a really interesting process because rocks are melting by going deeper into the earth, right? The pressure is actually increasing, but they're able to melt because they have that introduction of water. Now, coming back to our figure, again, let's say we're starting at point C, but now point C isn't necessarily increasing in pressure. It's not necessarily increasing in temperature. Remember, I did say that the water is going down to a deeper pressure. But the rock itself that's actually melting, the mantle rock that's melting, isn't going anywhere. So that rock at point C, the temperature isn't changing, the pressure isn't changing. All that's changing is the solidus is moving, right? It went from an anhydrous solidus to now water being incorporated. So that solidus moves. And now, even though the rock hasn't changed temperature or pressure, it's able to melt, right? Because the solidus moved around it. And partial melting at the water saturated solidus of peridotite, remember that's the mantle rock, produces a magma that's richer in silica. So it's about 58 to 68% silica when there's flux melting involved. And this silica-rich magma produces the volcanic rock known as andesite. Right? So you should be very familiar with mafic basalt and felsic granite. Andesite's that intermediate one right in the middle. And it looks like this, right? Basalt is black. Granite is really light shades of pink and white and gray. Andesite's in the middle. It's that mid-shade gray.